Hello, welcome to lecture 11 of EP1027, Maxwell's equations in electromagnetic waves. This is actually the lecture which was to be put out yesterday, but as I said, I got delayed the day before because of my voice kind of blew out. So this is the 11th lecture. Let's see what is in agenda today. Today's lecture will not be a very long lecture. Actually, I have just two topics to cover, but the principal part of it I'll spend recapping what I did in last lecture because I thought I went a bit fast. So I'll recap these phenomena. I'll talk about electromagnetic fields at the interface of dielectrics, which will lead to the laws of reflection and refraction, and also lead to equations for the transmitted and reflected amounts of electromagnetic wave, which is given by something which is in the Fresnel equations. And then I'll talk about electromagnetic fields inside conductors. We will see that in conductors and EM wave, which are oscillating electromagnetic fields, cannot make back progress, and they confine to the skin or some outer region of the conductor, which is known as skin effect. And I'll also talk about reflection from the surface of a conductor. So we will see that most of it will get reflected, and there is almost no transmitted wave. And then the new stuff today, which I will cover, is electromagnetic field in plasma. In particular, I'll talk about what happens in the ionosphere of the Earth's atmosphere. So this will lead to a phenomenon which will lead to something which is known as plasma frequency. There's a cutoff frequency below which the atmosphere or the ionosphere is sort of opaque to electromagnetic waves, and beyond this frequency, known as plasma frequency, it is transparent and it goes through. The fact that this is opaque and can be used to, actually it is used since the beginning of the last century for radiowave communication. This is how, so we'll talk about that. And then finally I talk about a celebrated phenomenon in optics which is known as dispersion. Most of you are familiar with this Cauchy's formula. We will see how this will follow from very basic considerations of electrodynamics. Okay, so this, by the way, Cauchy's formula, this is for dielectrics as opposed to a plasma. This dispersion applies to dielectrics, so there are no free charges. We will have to deal with bound charges which are bound inside molecules, and we will see the motion of such molecule in the response to EM wave passing through will lead to an effect which is known as dispersion. Okay. So these are the readings or references for this lecture. Griffith's chapter 9, everything is there. I think maybe plasma frequency he doesn't talk about, but then you can look up some of the other references and you'll find this, or even Wikipedia is a good reference. So let's talk about review of EM waves and matter. As I said, in Maxwell equations in matter in the absence of sources is given by these equations with the sources have been turned off. So no free charge here and no free current here. And then in addition, if you assume a linear homogeneous isotropic media, then we can use the constitutive relations to eliminate H in favor of P and D in favor of E. So we will get some equations for E and B fields explicitly. And then when you take the curl of these two equations, we are led to the wave equation in media. So we have a wave-like equation obeyed by both E and B, the same equation, except that the wave speed in this case for a material media is given by this form. Linear homogeneous isotropic media is given by this number, which can be written in another parameterization, which is this number. Usually epsilon is larger than epsilon naught and mu is larger than mu naught, so this is a number which is less than the speed of light, and that by what ratio it is less than the speed of light, that is parameterized by this number n, which is larger than 1, called the refractive index, which this terminology actually comes from optics, it is not native to electrodynamics. This terminology was developed before electrodynamics in optics, but since we will be covering a lot of optical phenomena, we might as well introduce this parameter. Then the energy density contained in such a wave which is passing through the media is given by this expression. Now in last slide, and maybe this last lecture slide, and maybe the slide before, the lecture before, someone had pointed out that this formula was wrong, and instead of d dot E I had d dot B. Please note that this formula is half d dot e plus half b dot h. And then if you use the linear homogeneous isotropic condition, you can convert d into e and then the h into b as well. So you get this formula. Energy flux rate is given by this formula 1 over E cross H, but then for linear isotropic media you can replace the H by B over mu, which I've done here. So this gives you the direction in which energy is flowing, as well as the magnitude of the flow is given by this. Now if we consider plane waves, then again we will arrive at the situation that plane waves are transverse in the media, just like in vacuum. EM waves in media are also transverse. K is the wave vector, so E and B are both transverse to K, as well as this will come from the Gauss law. These two laws will make sure that E and B are orthogonal to K, and then the other law, either using this Faraday law or this law, you can show that E and B will be orthogonal as well, given by this formula. So K, E, and B will again, just like in vacuum, form an orthogonal triad. The K is the wave vector, by the way. This is a unit vector, so you can see the magnitude of B is magnitude of V divided by the wave velocity, EM wave velocity in that medium, not C, which we had in vacuum. You have V here. Okay. The boundary conditions when this wave is incident on an interface of two media are something which we are already familiar with. As I said, this is without any charges, so everything is continuous. Not everything, but the boundary conditions which we wrote down are continuous. Normal component of E is not continuous, but this normal component of D is continuous. So this is a continuity condition for the normal component of D, normal component of B, and then the tangential components of E and H are also continuous. H I've written as B over mu. Okay. So using these, we will look at, because we have the boundary condition, we can now look at, we did actually in the last lecture, look at reflection and transmission of EM waves. So we had two media, which is specified by these values of electric permittivity and the refractive index. We could have used this permeability as well, but then these are all related. There's a relation between E, mu, epsilon mu, and N. So I'm using N in lieu of mu, permeability. So we have this situation which I mentioned in the last lecture, that there is an incident wave, and this is the wave vector for the incident wave. And then at this interface, which is given by the xy plane, or the z equal to 0 plane, there is some reflection and some transmission into the second medium. And in particular, I've drawn the in-plane polarization, which is to say that the electric field vector is on the plane containing the incident, containing the vector k as well. The plane of incidence. So this figure, actually, I do not have the right to draw this in a way which I've drawn here. This is actually a diagram from Griffiths, which I'm just trying to represent. Here I've assumed that the three wave vectors lie on the same plane, which is known as the plane of incidence. It is a consequence of Maxwell equations. We will see, but right now, since I have not gone there, I don't have any right to assume that. But it will turn out that the three vectors all lie on a single plane. As you know, two vectors, a vector defines, so three vectors will do not define a plane. In fact, this is a highly constraining condition, and it follows from the Maxwell equation. So what we assumed was that we have monochromatic plane waves incident on this interface from left. So this was the expression for the incident wave, as you can see. And the magnetic part I'm not writing. A magnetic part is something like this. You take the cross product of the incident wave vector with the electric field, and you get B. So I'm not going to separately write expressions for B. The reflected wave, we have a similar expression, except the subscript from I has changed into R. That's the only difference. Similar expression for transmitted wave. Again, the subscript is T for transmitted. And then, as I said, that frequency of the wave at such an interface of media will not change. The reason is that EM waves are actually as a result of emissions from atomic electronic transitions, in which you can think of the atoms as tiny oscillators which are oscillating when light hits them. And this oscillation frequency must match the frequency of the external force, which is the EM wave. Otherwise, this is what happens when you have a forced oscillation. That's why the frequency of a wave when going from one media to the other doesn't change. And this we will assume. And then as a result of which, because the frequency is the product of the wave vector times the velocity, and the velocity changes, the wave vector must also change, the wavelength also changes. But equating for the three of them, their frequencies, we get such a relation. So for the incident and reflected, the wave vector should be the same, magnitude of them should be the same because they're in the same media. The frequency and velocity are the same for them. However, the transmitted, it's in a different media, so this velocity of light and the velocity of EM waves in that media is different. As a result, we have this relation between transmitted. So the reflected wave vector magnitude is same as the incident, but the transmitted wave vector magnitude is equal to some ratio of the refractive indices times the incident. And then we write down the boundary conditions. And before we actually go into any detail, just by looking at the form of the boundary conditions, where we had some on one side electric and magnetic fields which are in this form, and the incident and the reflected, and then on the other side, second media, other side of the interface, we have the second media for which we have the transmitted components. Something like this. This can be written, since it is z equal to 0, the z component of this k dot x on each such exponent will go to 0. So we will just have the orthogonal case in the xy plane. So k parallel denotes the components of k in the along the xy plane, because the z component is 0. So when you dot it with the position vector, that kz goes to 0. So what we have here is such an equation, and just from this observation, because these are complex quantities, for these to be equal, the complex phases must be the same. Otherwise, there's no chance they'll be equal. And this must happen for all x and y and t. This is why it is so constraining, because it must be true for all x and y and t. At all points, the phases must be equal. You can balance sometimes when these phases will be the same and the sum of these two complex number will be equal to this, but it cannot happen for all x and y and t, unless of course the phases themselves are equal at all points. Okay, individual phases are equal at all points. So if you equate the individual phases at all points, the minus omega t term doesn't do anything, because it is equal by, it cancels out from both sides of the equation. However, the other part is contentful. So for phase to be equal, this quantity must be the same for k dot x, or k parallel dot x must be equal for all three waves, incident, reflective, and transmitted. So, and this is true for all x and y on the interface. So that means individually these vectors. So if you have two vectors, when dotted with a third vector giving you the same answer for all possible x, then the only choice is that these two vectors k parallel I and k parallel r should be the same. Okay, so this is a very tight constraint, because it is true for all x. So we have this situation. So the wave vector, or at least the parallel component of the wave vector, which is parallel to the interface, these components are the same. So this automatically tells you that the three k's will lie on the same plane. So the fact that the parallel components are the same, that means they lie on the same plane, x and y plane. Remember, x and y plane is orthogonal to this direction, so along this. Then we have kz, and then the k parallel. If k parallel is same, then the whole thing, which is the vector sum, is confined to this plane of the diagram. So this automatically, the phase equality gives you that these lie on the single plane, which is known as the plane of incidence. Okay, plane of incidence is the plane which contains the incident wave vector and the normal to the surface, normal to the interface. Now if this is so, I can write using trigonometry, with knowing the angle, various angles of incidence, reflection, transmittance, or refraction. We can write down the same statement in terms of the components of k. Not the component, I'm sorry, yeah. yeah, using trigonometry we can write it down. And then for the first equation, what we get is that because the k's are the same for incident and reflected, it's in the same media, so omega and v are the same, so that means k, which is the product of omega and v, they would be the same, so they cancel out, and we have theta I equal to theta r. So angle of reflection is equal to angle of incidence. This is a celebrated result which is known as the second law. Most of you are aware of this from high school or middle school. And then the second equation, which is between I and k, incident and transmitted, the equation that gives me the ratio of theta I to theta t is equal to kt over ki and magnitudes. But then kt is proportional to inverse the velocity, so kt is v2 and ki is v1, proportional to inverse of v1. So what we get is Snell's law of refraction. So v1, remember the refraction index is inverse proportional to the velocity speed of light, so v1 is 1 over n1 and v2 is 1 over n2, which gives you n2 over n1. Okay. So the incidence to refraction, the sign ratio of signs, is equal to the ratio of the refractive indices flipped in the reversed order. So in medium 1, medium 2, medium 2, medium 1, inverse ratio. So far we, as I said in the last lecture, to get to this point, the first two laws, we didn't even need any detailed Maxwell equations or anything, just the form of the Maxwell equation, the fact that it's a complex equation and we need to equate the phases, that was itself enough to give you these two. We can gain further information when we consider the full Maxwell equations, which are these, and this I will only perform for something which is known as the in-plane polarization, which I mentioned while I showed the figure before, which is that the E field is contained on the plane of the incident. And we can consider the component of E field which is orthogonal to the plane of incident. That will give you a different set of equations which we will not consider, and it will be left as a homework for you guys to figure out what happens. But let's consider the in-plane polarization. You have written here, indicated here in the title of the figure, the caption to the figure. And then you can imagine using the cross product rule, B for these cases, if E and K are on this plane, B must be orthogonal to the plane of the screen, so it is coming towards you. It is directed towards the person who is sitting in front of the screen. It is directed away from that, orthogonal to the screen. So B is off the plane. When you have E in plane, B is off the plane. So in plane polarization, so B is off the plane, so this is 0. The second equation is 0 identically on both sides because there is no normal component. B is in the completely in the let's say, yeah, B is completely orthogonal to the plane of incidence, so it has no normal component to the interface. So this second equation, which is basically no sources sinks law, doesn't give you anything. But the other three laws you can write using plane trigonometry. We can figure out what are the normal and tangential components of the electric and magnetic fields are, and we can write down these three equations. And then after we solve these three equations, which had actually three unknowns, and then we solve for the ratio of the reflected to incident wave amplitudes and the transmitted to incident wave amplitudes, and we found that they are written in terms of the various angles, alpha, which is a geometric quantity, and beta, which is made up of this fundamental properties of the 1 and 2 media. So beta is something which doesn't change with the change angle of incidence. Alpha is something which is a function of the angles, and this is given by this. And in particular, we notice that when alpha equals beta, when this happens, we have full transmission, because alpha equals beta, this quantity goes to 0 and we have full transmission. Only ET is non-zero, but this is going to 0. So what will happen is that the in-plane component of the electric field will be missing in the reflected wave. This doesn't happen for the off-the-plane polarization. So if the electric field is not in plane, but it is actually a linear superposition. You can think of a general electric field as a linear superposition of an electric field which is in the plane to off the plane, something like that. So this tells you that the in-plane polarization in the reflected wave for the booster angle of incidence will vanish, and the reflected wave will be completely polarized, and it will be polarized exclusively in the off-plane direction. Okay, so this is what happens a lot in nature. Most of the light we see in nature, when you're looking at the surface of a lake or anything, something reflected from the window pane, something like that, most of that light we see in nature are actually polarized, and this polarization happens because of scattering and because of this reflection from various surfaces. Okay, as you can see, this difference is a small number. It's a number which is which is smaller than the denominator, so the in-plane polarization is always less than the off-plane. Okay, now then we looked at EM waves in conductors. So conductors have free charges, and in particular we considered ohmic conductors. Ohmic conductors, the current density, free current density, is given by this relation, which is known as Ohm's law. And we substituted Ohm's law in the Maxwell equation for media. So we had Maxwell equation for media, and then instead of, by media I mean linear isotropic homogeneous. That would be our model, because otherwise we don't make much progress analytically. So we had the three Maxwell equation, which is Gauss law, Faraday law, and then no sources of Sinks law for magnetic fields. And then we had the Ampere-Maxwell law, except that for J free, I've substituted sigma E. Okay, so this equation looks a bit different from what we had in the case of dielectrics. Let me just go back. Yeah, for dielectrics we just had these two terms. Now due to Ohm's law, we have an extra term in this equation, which is this one. Okay. Now we then explored the consequence of this term, but before that we wanted to write down the continuity equation, which gives you the conservation of free charge. Conservation of free charge is given by this is the continuity equation, and in this expression for the divergence of J free, I substituted J free to be sigma times E, because that's Ohm's law. That is what J is in an ohmic conductor. And then this term became divergence of E, which is again divergence of E by using Gauss law, was rho free. So it gave an equation which is derivative plus del rho del free plus some number times rho free equals 0, and which has exponentially damped solutions, okay, exponentially decaying solutions. The solution to this equation, after you substitute this to be E and then use Gauss law, this is the dissipating solution. So any charge free charge which you push inside the conductor actually dissipates pretty fast. Now this fact we observed in electrostatics as well, that no volume charge resides, entire charge comes up to the surface. So any charge density which is inside the conductor quickly dissipates. This you can just show by using this continuity equation. However, this is true for an ohmic conductor. In particular, if sigma is 0, it will instantly go to the surface. So there's a time scale associated with this when this happens. So quickly, when I say quickly dissipates, there's a time scale given by the ratio of the epsilon to the conductivity. If the conductivity is infinite, this characteristic time scale of dissipation is 0. But that's only an ideal conductor. For ohmic conductors, we have a finite time after which there is not much charge left inside. So we will assume that there is not much charge left inside, so we will turn off the source term for the Gauss law, which we have done here. And then the Maxwell equation look like this. As I discussed, now you can take curl of these two equations and you get kind of a wave equation, almost a wave equation. We have this wave equation, but because of this term which is proportional to the sigma, we get a source term. So it's a sourced wave equation which has a source on the right hand side. Now to see what kind of wave solution is permitted by this kind of an equation, we fed an ansatz for a plane wave. So this is the plane wave ansatz, and we plugged this ansatz in this equation. And what we saw is that if we try to plug in a plane wave ansatz, we have to deal with the fact that this ansatz tells you that the square of the wave vector is complex. So it has a real part and imaginary part. That's why I put a tilde on top of these, because tilde usually will denote any quantity which is complex by this tilde. So we see that as a result of this sourced wave equation, which we have in conductors, the wave vector turns complex. So we can find out if the square is complex, so will be the k tilde itself. And in the case of sigma large, we can approximate these ugly expressions and make them simple, looking something like this. Okay, so if we plug this back here, if we plug this k back here, we will get an expression of this form. Okay, so this is the real part, and then the complex imaginary part, because of the double I, it became a minus sign. So what we have is that the amplitude is falling off with distance. So I forgot to mention that the plane wave solutions, the ansatz which we wrote down, is actually for a wave which is propagating along the z direction. And then just by plugging this in the wave equation, we get these. So I'm sorry, what am I doing? So this attenuation length is given by inverse of k. Remember, k has dimensions of inverse of wavelength or inverse of length. So kappa also has inverse of length. So inverse of this will give you the length after which you don't have the amplitude falls to 1 over 1/3. So after a few multiples of this wave, few multiples of this time, there'll be nothing left. So electromagnetic wave which is oscillating E and B field, if you make it incident on a conductor, it'll try to send you. If you try to send it into a conductor, through a conductor, it will quickly dissipate a few orders of length given by this quantity, which is known as skin depth. So if you try to, most of the EM wave will be confined to a very thin region close to the surface of the conductor, which is known as skin effect, right? So E and B, oscillating E and B fields do not make much progress inside a conductor. Gauss law. So this was just from the wave equation, but of course we have the full Maxwell equation, which are first order equations. Now these Gauss law and North sources of Sinks law, this will give you the same thing, that K is transverse to E and B. So K is orthogonal to E and B. So it is still a transverse law. It's transverse wave. And then you can use the Faraday law to show that if E is along X, of course B will be orthogonal to E and K, so it will be around. So K was along the Z direction, E is along the X direction, so B will be along the Y direction, because they will form a orthogonal triad. And then the difference with the dielectrics case is that because B is given by a cross of K and E, and K is a complex quantity, that means the phase of B will be different from the phase of E. Remember, the amplitude is given by amplitude. We get the kind of notation we're using is a complex notation for waves, in which the phase information is contained in the amplitude. The amplitude for B is the product of this complex vector K and E. So K is itself complex. So this will change the phase of E. So B will have a different phase from E. The ratio of the magnitudes, which is the real quantity, of course, is given by this magnitude. Just not the vector magnitude, but also the magnitude in terms of modulus of a complex quantity, is this ugly thing. But then again, as I said, sigma is very large. Typical conductivity of metals is around 10 to the 10, I think. So you can take this to be larger than anything, and you get this quantity. So the ratio of magnitude is given by this number. The phase lag, whether B is ahead of E, and by what amount, this angle is given by this formula. Okay, kappa and K are real, so you can write this formula. You can find out the difference between. So E and B, they are not on phase. They are not traveling on phase. The only good thing is that they're at least traveling orthogonal to each other, and phase velocity. What am I saying? And the energy is transported in the same direction as K. Okay, as the wave vector. So that is one good thing, but E and B are out of phase. Then we looked at the special phenomena in which wave which was coming from a dielectric medium is incident on the surface of a conductor. So we have an interface between a conductor and dielectric medium, and we had, of course, in order to find out how much of the wave from the dielectric is able to get inside the medium, get inside the conductor after being transmitted through the interface. For those equations, we will need to solve boundary conditions. So these are the boundary conditions at the interface between dielectric media and second media, which is the conductor. So this, as I showed in the supplementary notes, I only worked out for the case of normal incident. For that, alpha goes away, which is the angular parameter. So because it's normal incident, alpha is 1. And you had this beta, but the beta, the special thing about this is beta depended on k, which is on the other hand complex quantity. So beta will become the coefficient beta, which I had in the last slide for dielectrics, now becomes a complex quantity. So the reflected wave and the incident wave are not in phase, neither are the transmitted and the incident wave. They are also going to differ because the amplitudes, ratio of the amplitudes is not a real number but a complex number. Okay, so they're all out of phase. In particular, for a perfect conductor, you can show that beta will go to kappa 2, which is proportional to sigma. This will go to infinity, so you can neglect the ones, and so this ratio becomes -1, and this becomes 0. Okay, so this -1 means that the phase of ER is pi different from the phase of the incident. So this, again, you're already familiar with this. When you have reflection of a wave from a rigid surface, the reflected wave suffers a phase change of pi. So this is something which you're already familiar with, but here you have an explicit derivation, so that should be nice. And then there is no transmitted wave. So this points out to the fact, this is what it shows you, that conductors are excellent reflectors. Any incident wave from air or some other dielectric which is incident on the metal will get completely reflected. This is why metals are used for mirrors. As you know, most of the household mirrors are actually made of a film of mercury, which is then projected by a sheet of glass on top of it. So this is the reason. So because metals are excellent conductors. So this was more or less a review of what we did. So it still says review, which means because I'm reviewing what we did in the last class. Now I want to talk about two phenomena which are kind of impressive, which we will learn about. One is something of a phenomena which is known as plasma frequency. Now, what is a plasma? Most of you know a plasma is a ionized gas. For example, what we have in the ionosphere due to solar radiation, a lot of the molecules or atoms get their electrons knocked out of the atoms, and it becomes gas which is full of ions and electrons. So this is kind of an ionized gas in which the constituents are not atoms, but instead they are ions. This is called a plasma, and it is, plasma is the phase of matter which is most abundant in the universe. So this phenomenon is actually very common all over the universe. Of course, in terrestrial scales, it is not that important because Earth is not a typical corner of the universe. Most of the universe is actually not in the form not in the form as the planet Earth, which is composition is completely different. Anyway, so this ionized gas is there in the atmosphere, in the ionosphere, and this is how this phenomenon was actually discovered. So what happens is that we will only focus on the electrons in the plasma because the ions are very heavy and they're not as mobile as the electrons. So the primary current carrier would be the electron, and this is what we will focus on. So what I have here in this equation is it's a free charge, and then it was acted upon by an electromagnetic wave which is passing through that plasma. So the equation of motion is just this Newtonian equation. Mass times acceleration equals force minus E times the electric field, electric force. So here I've used a form of the electric field which is oscillating, which is what happens when you have an EM wave passing through. and see that I've actually dropped the kx part because that won't play much of a role. So when we plug this in this equation, the solution is very simple. Solution we can show very easily is this. Otherwise, alternatively, you can also plug this in and check that indeed this is the solution. Okay, plug this in here and check that both sides will match, and this is the solution. So whenever you have an oscillating electric field, the position vector also oscillates with the same frequency, and then there is the some constant which gives you some amplitude of the oscillation. Okay, so the amplitude of the oscillation is inversely proportional to the frequency. Now we can find out the current density due to this EM wave. The current density, most of you know, is given J equals rho V. V is the velocity, so rho times V. Now in the atmosphere, in the ionosphere or some plasma, if n is the number density of the electrons, so the charge density would be number density of electrons times the charge of each electron, so that is n times minus E. This is what I've written. And x dot is this quantity times derivative of this quantity. Time derivative will pull down a factor of this minus I omega. So this is what I've done here, the same quantity except this x dot means this minus I omega is here. And then this will lead to an equation which is like this, which is some imaginary number times the electric field, E. So this combination is the electric field, E. So this looks like Ohm's law. This looks almost like Ohm's law, except there is a huge difference. The conductivity, the conductivity constant is the imaginary quantity, purely imaginary quantity. So that's why I said this is not a real conductor in like a metal, where conductivity is a real constant. Instead, we have here is conductivity is an imaginary constant. So this happens for a plasma or an electrolyte. Now, we had already an equation which where we had written down for an ohmic conductor, the wave vector for an ohmic, or the square of the wave vector for an ohmic conductor. A few slides back, we had already written down the equation for the wave vector for an ohmic conductor, EM wave passing through an ohmic conductor. So since this is also kind of ohmic, we can use that formula, with sigma being a completely imaginary quantity. So we plug in what the sigma is, conductivity is here, and because sigma is imaginary, I times I, this will get real. This will become real. Although it is real doesn't mean it is a real wave right now. Remember, this is the difference. So it only makes sense when k is real, as well as k squared is real, as well as positive, that the wave vector will be positive. And if this is negative, then of course this will be purely imaginary. So we have two situations. So if I plug this in here, we can rearrange everything and write it in this form, which is this constant times mu epsilon constant times omega square times this factor minus 1 minus omega p square over omega square, where omega p is related to this constant. Now, from this equation, it is very simple to deduce that if omega is greater than omega p, so this number will be less than 1, this number will be less than 1, and you have a positive thing, so there will be a wave with a real wave vector. On the other hand, if we have a omega to be less than omega p, less than omega p, then this number is greater than 1, and you have a purely negative quantity. Since the square of this is a purely negative quantity, what you will have is k tilde to be purely imaginary. So if k tilde is purely imaginary, there will be no oscillation. Instead, there will be complete attenuation in time, so the wave will decay completely. So the entire energy of the wave, EM energy, will be lost in some kind of, not Joule heating, but a similar phenomena occurs in plasma that will be delivered, and the electromagnetic wave will get extinguished. There is no way attenuated. It doesn't make into the atmosphere. So this is exactly what happens in the atmosphere. So remember this thing: if it is below the plasma frequency, then it gets attenuated. On the other hand, if it is more than the plasma frequency, it goes through. Now, this fact was utilized in radio communication at the beginning of the 20th century. So, what happens is that when it, as I said, if omega is less than WP, there is no transmission. And in fact, the full wave is actually reflected back, or part of it is reflected, and that can be used to communicate from one place in Earth to the other by bouncing using the ionosphere as a reflection, as the reflecting sort of surface. So waves get reflected off the ionosphere and back to the Earth at some other location. So this is how radio communication works. And if you use the number density of electrons in the ionosphere, of course there's a variation of over 100 times. So I think this goes from 10 to the 10 to 10 to the 12 or something like that. 10 to the 10 to 10 to the 10 to the 9 to 10 to the 12 or something like that. No, I'm sorry, 10 to the 10 to 10 to the 12, yeah. For the mean value, if I take some kind of average value of the ionosphere electron density, and I plug this here, rest of these are fundamental constant. Of course, I'm taking the ionosphere to be almost transparent, so, the permittivity to be equal to almost 1. Not 1, I'm sorry, as same as vacuum permittivity. I'm psychologically still thinking in terms of CGS unit. That's why for me epsilon is 1. But anyway, in SI unit this will be equal to epsilon naught. And then you can compute using this value, nominal value of the electron density in the ionosphere. You can compute the plasma frequency for the ionosphere, and it will turn out to be of the order of 20 megahertz. Actually, because there is a flag factor of 2 spread here, you'll get, this is basically true for 1 to 30 megahertz. I think this also has a spread or a range. So between this range, if you can communicate with your friend through a radio waves by bouncing radio waves off the ionosphere. Okay, so so this is something which is known as plasma frequency, something perhaps in some of you have already heard it in high school. Some of you might not have, so this is the time you get to know about this. It's an extremely cool phenomena which was discovered by amateur, I think, radio astronomers sometime back. Not radio astronomers, but radio itself, radio telegraphy itself was in its nascent stage in the early 1900s, 1910, 1912, I think, and then they figured out, and then somebody came up with a theoretical explanation of why this is happening. And this is happening because of this phenomena which is known as this plasma frequency. Okay, then the next thing, this was about plasma. And we go back to dielectrics in order to cover a topic which is again also very common in theory of optics. Most of you have learned about this in school. I know we did some kind of experiment back in high school on this. So the idea is that when you have dispersion of waves is that when you have a wave which is made up of different frequencies, not a monochromatic wave, but a polychromatic wave, when you have different frequencies and they all travel with different phase velocity. So remember, the phase velocity is given with the frequency divided by the wave vector k. And if this becomes if this ratio is a function of k, then we call that we will call that phenomena to be dispersion, because each of them will initially they'll all separate out. Now this happens when light enters from air to a dielectric substance such as a glass of water. Most of you know that colored through the prism. Most of you know about this experiment in which you can actually see that happening because the speeds are different. Snell's law says that their angles of refraction will turn different, and they will get refracted at different angles. And this difference you can actually check and see in the lab. So dispersion really happens. For dispersion, you can also show that the amplitude of the wave, of this packet of wave, a combined packet of wave of different frequencies, is traveled with a speed d omega dk. Okay. This you can easily show by doing a superposition kind of an argument. You have a bunch of waves with different amplitudes, different frequencies, and different speeds. And if you add them up, if they're the velocities, if the frequencies are close by, omegas are close by, not too far apart, then you can show that by doing Taylor expansion that the mean waves travels with some mean omega and mean k. while the amplitude travels with this derivative differential. Okay. So what is the theoretical picture of optical dispersion when we have in optics? Again, we will consider the electron picture because that is helpful. It's a very classical picture, but it still works. So theoretical picture of dispersion is based on this model, forced oscillation of electrons inside molecules. Remember, inside dielectrics, we have bound charges, okay? So the electrons are bound inside molecules or atoms. So they're orbiting this, they're moving inside these molecules. They don't have freedom to go beyond that. So this is a typical equation of motion for the electron, what it looks like. So you have the electric field will try to stretch it away from the molecule and then pull it away from the molecule. And then there'll be a restoring force because the electron is bound by molecular forces which will try to bring it back. And there is also some kind of damping. Not all the directions in the molecule are same, and in some directions it will face some kind of stiff opposition or damping. So there is a damping constant as well, although this will turn out to be very small, but it's still non-zero. So we have this kind of an equation, and the EM wave which is passing through I have written again just by the time fluctuating part. Spatial fluctuating part will not play much of a role here. So this is the equation, and again most of you can guess this equation has a simple solution. So again you try answers because we know that a forced oscillation x will also be something of this form, x0 times e to the I omega t, and x0 is given by this solution. Okay. So suffices to consider 1D motion, so it's actually a 3D motion, but just for simplicity we will consider one dimension. You can think of this motion in the radial direction, of the radial coordinate r. Okay, so it will turn out that the amplitude of that is given by this, and then the oscillating part is given by the phase. Okay, so this is the full solution. I'm sorry, I don't know why I have written to be x naught 0, because 0 usually means to the amplitude. That is already given by this this part. So this is, if you consider this to be x0, this should not be there. And if you consider it to be just x, then this is your complex amplitude. Now, of course, when E is 0, this is 0. So this is actually deviation from its usual path in the molecule. So this is the deviation from the usual trajectory of the electron inside the molecule. Because when you remove this, this becomes 0. So there is a, I have not, the homogeneous part I have not written, which is the solution when this is 0. But so this is the difference from its equilibrium situation. Now this will lead to a dipole moment because the center of charges, it is getting away from the center of charge. So this will lead to a dipole moment which is given by the electron charge Q times x naught. So Q is minus E, by the way. I've written Q because I'm talking about a general charge, I guess, but Q is equal to minus E for the electron. So this is this electron, because of its shift in orbit due to the EM wave passing through, will lead to oscillating dipole moment. And then we can consider the full dipole moment of the entire dielectric or solid, dielectric solid. So we have to sum over all electrons. So we have to sum over this P over also the electrons inside one molecule. This is what I've done. So this is x naught, by the way. This is for electron which had its natural frequency domain omega naught, but then there are many electrons inside a molecule, and each of them have different characteristic frequency, which is that, and I've summed over all such electrons in the molecule. And then we have to sum over all molecules. So that is done by this coefficient n. So this is for a single molecule, and then you multiply by the number of molecules per unit volume. That gives you the dipole moment per unit volume, or the polarization, right? So this is how we define polarization: dipole moment of a single molecule times the number of molecules per unit volume. That gives you the dipole moment per unit volume. So also this Nj, which was not there, we had just Q over M, which is of course there, but this Nj is because there might be multiple molecules with the same frequency in a single, multiple electrons in the same molecule with the same characteristic frequency. You can take this to be 1 as well, but let's keep our mind open and let's allow many different electrons in the molecule with the same characteristic frequency omega j. Okay. Now, since P is given by this formula for dielectrics, epsilon naught times susceptibility times E. So from this, if I divide both sides by E and by epsilon naught, I get the susceptibility. From the susceptibility, we notice because of this, it's the complex object and it depends on omega. So susceptibility and hence permittivity is a function of frequency omega. So remember, the relative permittivity is defined as 1 plus the susceptibility, and which is given by this formula. So permittivity is a function of frequency. So a refractive index, which is given by the relative permeability times relative permittivity. In most material media, it turns out that mu and mu naught are almost the same. So I will take mu to be almost same as mu naught, and most of the difference is due to the difference between epsilon and epsilon naught. Okay, so this term I will drop because they are almost the same. So we cancel out and give you 1. And then we have ratio of epsilon to epsilon naught. But then epsilon, as I've seen, is a complex quantity which depends on omega, which is complex quantity and it depends on omega. So to define the refractive index, we will actually need to consider the real part of this ratio. Okay, the real part of this. So this is the complex permittivity or complex dielectric constant, and we have to take the real part of it. That will give us the relevant index for optical index. Okay, what we measure in the lab as the refractive index, which is given by this formula. So you can write down the real part of this guy, which will be this. Okay. Now again, so the refractive index is a function of omega, because as you can see, omega appears here. So refractive index is a function of omega, means that the speed of the wave, which is given by c divided by the refractive index, is also, the speed of the wave is also a function of omega. This is what we define to be dispersion, right? The speed of the wave, if it is function of k or omega, then we have a dispersive media. So different frequencies will travel with different velocities, and hence it will lead to this phenomenon of dispersion. Now you can plot this. You can plot this as a function of omega, and it looks something like this. Okay, so as you can see, it has some sharp peaks and plummets here, something like that. But these are actually the frequencies or characteristic frequency omega j's. Okay, but when it is far from the characteristic frequencies, when it's different from, for example, this region, when it is much less than the, actually the molecular frequencies are very large compared to the frequency of the light which we usually send in the media. So we are actually most of the time in this region. So this is the region. Then you can make the suitable approximation of this function, which looks something like this. And you can see it has a refractive index actually increases with frequency. This happens here as well. You can see in this region also, apart from this 2, 3 which I have denoted, which are the locations of the omega j's, the natural frequency of the electrons. If you are far away from it, then the trend is that the index, which I plotted along vertical axis, and the frequency, it actually increases with omega. It increases with omega. Okay, so this is known as normal dispersion. And you can show that if you neglect the damping in particular, then this equation boils down to something like this. This is a fundamental constant. It can be lumped into this number a, and whatever this coefficient is, another some fundamental constant which can be lumped in, not a fundamental constant, but a constant depending on the medium itself, depending on the molecular specifications of that particular medium. So you get some constant plus b omega square. In terms of wavelength, if you write this, omega square would be inverse of the wavelength square. Now this formula is something which you must have verified in the lab in high school. I don't know if it's still there in the syllabus for the lab experiments, but at least I think if not there, you will do this in some physics lab here. You can check that indeed this normal dispersion formula, which is in this part of the curve, you do see a quadratic increase in the refractive index as you change omega, or inversely with the wavelength. However, as you can see, the behavior is completely different when you're anywhere in the vicinity of these characteristic frequency omega j's. So when you have omega j, there is a difference. These two terms become very small, and there is a sudden plunge. So approximately omega j, any of these resonant frequencies or natural frequencies of the oscillations, then the index suddenly falls. Instead of increasing, it suddenly plummets. Right? So again, it was increasing for a while, and then as the next resonant natural frequency is approached, it suddenly plummets, and this behavior goes on for a while. So this behavior is known as anomalous dispersion. This is far from, as opposed to anomalous, as opposed to something which is normal. So for most part of it, it increases, but then whenever you're in the vicinity of these characteristic frequencies or natural frequencies of the electrons inside the molecule, the index plummets suddenly. Okay. So this behavior, again, you can simplify this expression using some kind of Taylor expansion around with the small difference, and you can show that refractive index in fact decreases by this amount. So if you increase omega, this actually falls down. So this describes this plummeting part. As you change omega, this falls. This fall is explained by this, or modeled by this kind of an equation. You can check. So this very simple picture we had of an electron inside a molecule obeying a one-dimensional motion, that actually reproduces this experimental curve very nicely. All the behavior of this, of course, the coefficient might not match, but qualitatively, this is what is going on. Qualitatively, this formulae actually do represent what we observe in the lab, that the refractive index first increases, and then if you keep on increasing, all of a sudden it plummets. Okay. So this is the theory of dispersion, or as I would say, a microscopic theory of dispersion, classical macroscopic theory of dispersion. So I will stop here, and in tomorrow's class, I will completely pick up a different topic. I think we've more or less exhausted the topic of EM waves. And tomorrow's class, what I'll talk about is about the radiation emitted by charges. As I said, radiation is an important part of this course. So we will try to find out what are the fields produced by a moving charge, which are potentials and the fields produced by a moving charge, something which is known as Linear-Wishart potential, and then the field equations. And then we will try to see the various radiation patterns for different kind of motions of the charges, uniformly accelerated motion, uniform motion, and so on and so forth. Okay, so I will stop here, and tomorrow we take up the topic of radiation emitted by charges. Okay. Oh, I wanted to mention before I say bid you goodbye that if you have any questions, please send me an email of your queries, or if you want to set up, if you have more queries and if you want to set up a Google Meet appointment, that is fine. Please send me an email and I'll find a suitable slot where we can chat. Okay, I'll see you tomorrow with a new lecture.